So we try to understand how we derive Miller Bravais indices for the hexagonal closed pack system. And we know that in this case we have a coordinate frame made of 4 axes, and this becomes tedious to learn, as we have seen in the class discussing about it. And it's much easier to use, instead of having right projections like we tried in the class in the example there, in the first example, much easier to work with the third 3-axis coordinate frame and then transform into a 4-axis coordinate frame by using this simple math that can also be automated with the software program. So again, just to refresh our memory, we have in this case the hexagon that we are talking about at the base. It's considered an equilateral hexagon, and then because we want to imagine that a hexagon, an equilateral hexagon, we know that the edge of that is equal everywhere, and also the radius from the center right here. If we'll have to inscribe this hexagon in a circle, that will be the radius of the circle, and that radius will be also equal with the side, with the edge, basically. So like I put here, if the edge is 1a, say that's whatever it will be, the length of the cube of the cell, then the radius also will be a. In this case, when we select the 3-axis coordinate frame, we drop, suppose in this case, the A3, and we keep the A1 and A2, and then the Z-axis. And we try to find for this that you see here, this direction, that they derive it as a 1 bar 0 0. We try to find how did they got these Miller Bravais indices. We try to find that out. So again, like in a right coordinate frame where the angle at the center it was 90 degrees, in this case it's not. It's 60 degrees, as we can see there, between the 2 axes. We are trying, when we solve, we try to get from that point parallels to the axis to see what is the the coordinate along the A1 for this vector, for this direction. And let's consider this vector as they would do there. So if I want to get a parallel there, like we can see here, we can draw that parallel with the axis, and we see that if this is one unit, a unit of A, 1a, this right here coordinate will be half of that. And probably it's much easier to, instead of using working with fractions like 1/2 here, 1/2 there for the other A2, the other coordinate, it's probably easier because we talk about directions, not vectors here. We consider the vector going all the way here. That way the coordinate, when we draw the parallel from this tip, will be an integer 1a, not a fraction 1/2 a. So it's because we get the same way. You can work it out if you want from here to 1/2 a, and you will get the same Miller Bravais indices. So in that case, if we elongate that, we can see that the coordinate, if you draw a parallel from this point there all the way to that A1 axis, then we can see the coordinate in that case will be 1a. And this parallel is to the other axis A2. Again, the same way, if I draw a parallel from here to find the projection parallel to A1, to find the projection on A2 there for that point, I will figure out that is also 1a, but is in the negative direction because the positive as we selected is in that direction. So it will be minus 1a. So now we come back to figuring out that, so that is for us, it will be 1a here, minus 1a there, and there will be a 0 because this vector, it doesn't go along the z-axis, just in the base there. So that direction, so there will be the 0 along the z-axis, the projection. And if we are normalizing, in other words, we drop that a, we divide it by a, 1a divided by a, we get a 1, minus 1a divided by a will get us minus 1, and here we have 0c divided by c will get a 0. So we drop the lengths along those. And we can see that we get those projections like capital U, there will be 1, capital V will be -1 for that, and capital W will be 0. So now we use these relationships and we can see easy math. We have 1/3 2 times capital U, which we said 1, minus, and here we have a -1 there. And when we draw, we solve, we get 3 divided by 3, and then we get reduce the fraction here, and we get 1. Similar thing we do for V, and you can see the relationship is nicely drawn. So you have 2V when you talk about V, you have 2U when you talk about U. And for the fourth axis, we get negative of this small u plus small v, what we got here. So in other words, we have basically a small u, it's going to be a 1, a small v, it's going to be a -1. When we add them together, we get 0. So, and w is probably the easiest because small w it's equal with large w, capital W, and it's equal with 0. So we can see that now we have 1, -1, 0, and 0. And as we recall, we put the negative sign on top as a bar, so we have 1 bar, 0, 0 indices. I hope this clarifies, and it's simple for us to see that we use vector directions. We can elongate the vector if needed, or if we like it, we can work with the fractions there, like we said, 1/2, so we would have ended up here with 1/2, -1/2, and a 0 again. So when we do the math, we still get the same result. If we have to simplify the fractions, reduce the fraction, we still will get 1, -1, 0, and 0. Hope this helped. If not, please let me know in an email, and I hope you have a beautiful day.